In this video, we're going to be talking about the Brayton Refrigeration Cycle. It's also known as the Reversed Brayton Cycle or the Joule-Coleman Cycle. They're one and the same thing. Within this Reversed Brayton Cycle, we're going to be using our working fluid, which is going to be gas. So our working fluid is going to be gas, and more often than not, it's going to be air. This cycle is going to contain 4 subcomponents at the very basic level, and that means that we're going to have, first of all, a compressor in which the gas is going to be compressed, so work is going to be provided into the compressor. After the gas has been compressed, so we've got gas which was at low pressure. It's been compressed isentropically from state 1 to state 2, and from state 2 we've got a heat exchanger over here, which is a condenser. So within this condenser, we're going to have heat rejection that's going to take place. So we're going to have Q dot out over here at constant pressure, and we're going to have a turbine attached to this condenser, and this turbine is going to generate some kind of work. So that's work done by the turbine. And then we're going to have state 4 on the other side of it, and then we are going to have another heat exchanger here, which is usually called an evaporator. Again, at constant pressure, we're going to have heat addition that's going to take place here. That's Q dot in. So you got process 1 to 2, 2 to 3, 3 to 4, and 4 to 1 that need to be analyzed. Across this, you could also make a TS diagram. Let's just make a TS diagram. And on the TS diagram, you're going to have constant pressure lines, which I'll just represent by these. These are my constant pressure lines. So process 1 to 2, and right now remember that we're only talking about the ideal Brayton cycle. So with the ideal Brayton cycle, we're going to have reversible processes. All 4 of these are reversible processes, and because process 1 to 2 is an isentropic process, that means that no heat addition is taking place as well, and I can just write it as a reversible adiabatic compression because the gas is being compressed within the compressor. So reversible adiabatic compression from state 1, which was at low pressure, to state 2, which is now going to be at a higher pressure, and compression is always in the vertical direction on the TS diagram, vertically upwards. So that's process 1 to 2. And then process 2 to 3 is reversible, and it's going to be at constant pressure, so it's isobaric, and it's going to be heat rejection. So that's going to be on this constant pressure line until we arrive at state 3. And 3 to 4 is again going to be an isentropic process, and that means it's going to be a reversible adiabatic, but this time because it's within the turbine, so that means it's going to be expansion that's going to be taking place. So it's going to be 3 to 4 vertically downwards because we're saying it's expansion. Expansion on the TS diagram is vertically downwards, and 4 to 1 then is going to be reversible, again isobaric, heat addition this time because heat is being added into the evaporator, and that's going to complete our cycle. Okay, so for all of these processes we could go ahead and write down the equations as well, and the equations are going to be for the work done, for the heat rejected, for the work added by the turbine, generated by the turbine, and the heat that is added into the evaporator. all of these are going to be in terms of m dot into delta H, which is enthalpy. So work done, if you're looking at, let's say, across the compressor, that's going to be work done across the compressor. It's going to be equal to m dot into delta H, which is going to be between state 1 and 2. So is it going to be H1 minus H2, or is it going to be H2 minus H1? So a good way to figure that out is if you look at this arrow direction, because it's pointed inwards, so it's going to be final state minus initial state. So it's going to be m dot into H2 minus H1. Okay, and then within the condenser, this heat rejection you could write as Q dot out. It's going to be in terms of m dot into, and now because the arrow is pointed outwards, so it's going to be initial state minus final state, which is 2 minus 3, so it's going to be H2 minus H3. And with the adiabatic, reversible adiabatic expansion that takes place within the turbine, let me W dot T subscript T equals m dot, because the arrow is pointed outwards, so it's H3 minus H4. And then the heat addition within the evaporator, that's going to be Q dot N equals m dot into, and now it's going to be, because the arrow is pointed inwards, so it's going to be final state minus initial state, which is H1 minus H4. Okay, but now if I was treating my ideal my working fluid as an ideal gas, then I could simplify this even further, because for an ideal gas I know that the relationship delta H equals Cp into delta T is valid. I guess Cp is your constant specific heat. And now I can equate it in terms of, so it's going to be m dot into Cp, which is your constant specific heat, into T2 minus T1. And so I can write all of these just like that: Cp into T2 minus T3, m dot into Cp into T3 minus T4, m dot into Cp into T1 minus T4. Okay, so all of these are only valid if the working fluid is being treated as an ideal gas. Now, for a refrigeration cycle, we usually look at its performance in terms of the coefficient of performance, and the coefficient of performance is going to be equal to the refrigeration effect that is produced divided by the work done across the cycle. And the refrigeration effect in this case, if you don't know what it is, then you could imagine that you have a reservoir here or a room that you want to cool down. So that means you have to take heat out of this room. That is going to be this Q dot in here, because it's actually Q dot out of the room and Q dot in into the evaporator. Okay, so that's how the room is going to get colder, right? If you're going to be extracting heat out of the room. So this is the heat that you're extracting out of the room, or the refrigeration effect that you're producing in the room. So it's going to be, your refrigeration effect is going to be Q dot in, or I could just take this m dot onto the other side, and it's going to be divided by m dot divided by work done across the cycle is going to be the work that you provided for compression across the compressor. It's going to be work done by the compressor, provided to the compressor, minus work generated by the turbine. And so I could write this in terms of enthalpies, which will be H1 minus H4 divided by H2 minus H1 minus H3 minus H4. But again, if I was treating my working fluid as an ideal gas, then all of these could be replaced by temperature, because m dot and Cp would get cancelled out in the denominator and numerator. So it's going to be T1 minus T4 divided by T2 minus T1 minus T3 minus T4. Okay. So now we've looked at the ideal Brayton refrigeration cycle, but what if we wanted to look at the actual Brayton refrigeration cycle? In that case, we would need to introduce the reversibilities in here, and what kind of reversibilities could occur. So we've got entropy on the x-axis, and that means that usually with every process, entropy would have to increase, especially the ones where we've talked about the isentropic processes, which is process 1 to 2 and 3 to 4. So in these processes, right now, they're reversible. By introducing irreversibilities, they're both going to be non-isentropic compression and expansion processes. That means these would have to change. Other than this, we would have pressure drops in the cold and hot heat exchangers, so in the evaporator and the condenser. Usually we neglect the pressure drops and we account for the account only for the non-isentropic compression and expansion processes in the compressor and in the turbine. So let's just take a look at that now. So if we take a look at the same cycle now, I've just shifted over everything here now. This is the same TS diagram. I've got the same processes. Process 1 to 2 is in the compressor. It's an isentropic process. Process 2 to 3 is in the condenser. 3 to 4 is in the turbine. Again, isentropic. 4 to 1 is in the evaporator. So, like I was saying, we've got irreversibilities that are going to be taking place. So looking at, first of all, this compression process, what's actually going to be happening is that the entropy is going to increase, and entropy is increasing in this direction. So for it to be non-isentropic, this process would have to start at 1 and finish at 2. This is the constant pressure line. All of these are the constant pressure lines. So eventually I'm going to be here at 2 dash. So from 2 dash now, for the irreversibilities to take place in 2 to 3, now this process wouldn't actually go from 2 dash to 3. It's not going to be a constant pressure process, and eventually I'm going to have a reduced pressure at 3, and that's going to be my 3 dash, you could call it. Okay. And then from 3, when it's going to go down again, entropy is going to increase. It's not going to be isentropic anymore, and entropy is increasing in this direction. That's why it's moving inwards now. It's going to be my 4 dash is going to be here, and from 4 dash I'm going to come back to 1 because it's not going to be a constant pressure process now. This is the constant pressure line. So if it's jumping the line, then it's not a constant pressure process. Okay, so it's going to jump the line, and it's going to eventually end up back at 1. Okay, so this is how this cycle is going to look like. And if we look at the compressor, then the isentropic, so the efficiency is going to come in now, because this is the ideal process, 1 to 2. 1 to 2 dash is the actual process. And so we usually write it in terms of efficiency, which is known as the isentropic efficiency. Subscript C is for the compressor, and isentropic represents the isentropic efficiency. It's going to be in terms of the actual by ideal work done, or in terms of the ideal work done, which is the isentropic work done. So work done by the compressor when it was the isentropic process, and work done by the compressor when it was the actual process. And the isentropic process is 1 to 2, so it's H2 minus H1 divided by H2 dash minus H1. But if we were treating it as an ideal gas to working fluid, then it would be T2 minus T1 divided by T2 dash minus T1. And just like that, we could also write the isentropic efficiency for the turbine. So subscript T represents the turbine, and that will be in terms of the opposite now. It would be actual by isentropic. So turbine work done, the actual work done, divided by the turbine work done, the isentropic work done, and that's going to be in terms of H3 minus H4 dash, because it's process 3 to 4. H3 minus H4 dash divided by H3 minus H4. And if it was an ideal gas to working fluid, then it would be T3 minus T4 dash divided by T3 minus T4. So if we were writing it in those terms, then we would have to not only, obviously we would have to find the enthalpy or the temperature at state 2, and then we would have to find out the enthalpy or the temperature at state 2 dash, and that would then change the definition of the coefficient of performance as well. So then the coefficient of performance would be, which was H1 minus H4, that would become H1 minus H4 dash for the actual process, and divided by, that would be H2 dash minus H1 minus H3, you got minus here, minus H4 dash. Or you could also write it in terms of temperatures if you were looking at the scenario where the working fluid is being treated as an ideal gas. Another thing that we see from this cycle is that the refrigeration effect is going to reduce because the irreversibilities that have been introduced, because one, the work done has increased, so because the coefficient of performance is in terms of the refrigeration effect by the work done across the cycle, so that means this has increased. So the work that you're providing to the compressor, that has increased. The work that the turbine is generating, that has decreased. So over here, that effect takes place. The refrigeration effect over here between 4 to 1 or 4 to 1 now is 4 to 1 now. That means the refrigeration effect has reduced as well, and that means that the coefficient of performance of the reversed Brayton cycle, or the Brayton Refrigeration Cycle, or the Bell-Coleman Cycle is going to be a lot worse off as well. Now I want to go back and take a look at this scenario where we are talking about the working fluid being assumed as an ideal gas. This is known as your cold air standard analysis. So if I write it here, this is going to be my cold air standard analysis. And within the cold air standard analysis, I also need to relate the temperature ratios right now, because if I know temperature at 1, then how do I find out the temperature at 2 if all these are unknowns? So then in that case, for isentropic processes, we have relationships that are available because of the constant specific heat assumption that we make here. And that is that I can relate, so I've got this as my isentropic process and this as the isentropic process. So for these two, I can write the temperature ratios in terms of pressure ratios. So it would be T2 by T1, and that's going to be equal to P2 by P1, and that's going to be to the power K minus 1 by K, where K is your specific heat ratio. Okay, so this is your ratio of Cp to Cv, and usually for air it's taken as constant, so it's going to be 1.4. And then for process 3 to 4, I can also write it in terms of T4 by T3, just as I've done here, equals P4 by P3, and that carries the power K minus 1 by K. Okay, and then P4 by P3 is actually just P1 by P2. Why is that? Just look at this. These are constant. This is a constant pressure line, so P1 is at the same pressure at P4 as P4, and P2 is at the same pressure as P3. Okay. So this is my cold air standard analysis. But if I was doing this analysis over here, then this is known as the air standard analysis. And for the air standard analysis, these two relationships that I just wrote are not valid anymore. So over there, we have to then go and use the tables, because we use a relationship for something known as reference pressure or relative pressure. And I'll just write it down here. So if I was talking about the air standard analysis, then with the air standard analysis, instead of being able to use the two equations that I wrote previously, I would be using relative pressure terms, which would be in terms of PR2 subscript R2 divided by PR1 subscript R1 equals P2 by P1. And then for the other process, it would be PR4 subscript by PR3 equals P4 by P3, or again we could write it in terms of P1 by P2. So this relative pressure over here, it's actually not even a pressure because it's a ratio. So we just call it relative pressure. It's not actually a pressure. It doesn't have any units like that.